companies manufacturing highway emergency flares. Such flares are supposed to burn for an average of 20 minutes, ideally. Every hour, a sample of flares is collected and their average burn time is determined. If the process is working correctly, 68% of the time, a fairly decent chance that the average burn time is going to be between 14 and 26 minutes. And do notice those two numbers have an average of 20. So I guess that's kind of their justification for saying the average burn time is 20. But still a fairly high percentage, 32, burn longer or shorter, longer than 26 or shorter than 14 minutes. The quality engineer in charge of the process believes that if 4 out of 5 samples fall outside these bounds from 14 to 26 minutes, then that's a signal that the process might not be performing as expected as far as like manufacturing the flares is what they're getting at there. Maybe there's something wrong with the manufacturing process. That's kind of the idea of quality control. You're doing sampling. In this case, you got 5 samples. If 4 out of the 5 have an average burn time that's not inside that range, that's a signal that maybe something's wrong with the manufacturing process. Something might not be performing as expected. Each morning, the sampling begins anew. Let X denote the number of samples drawn in order to obtain the force sample whose average value is outside the above bounds. So that would be, not working properly, so to speak. Find the probability that if for a given morning, X equals 5, and hence there seems to be a problem that's detected. With negative binomial, so again, contrast this with binomial. With binomial, you have a fixed number of trials, n, and you are counting the number of successes, x. X could be anything from 0 to n, like shooting free throws. Say with 10 attempts, how many do I make? With negative binomial, it's like reversed. Now you think of the number of successes you're after as being fixed. And the number of trials being the variable. How many trials will you need until you have a certain number of successes is the way our book phrases it. Actually, other books, and I'll show you another book here, phrase negative binomial distributions differently. They think of them differently. Okay. That other way with the other book I'm going to show you is actually more related to how the technology with spreadsheets and Mathematica does it. So X is, again, the number of samples to obtain the force sample whose average value is outside. X being 5 means you get 5 samples when the force sample is outside that range. Being outside the range is supposed to be success here, even though it sounds bad. Another confusing thing about it. When we talk about Bernoulli trials, success and failures, yes, often success is a good thing and failure is a bad thing, but not always. Here, success means it's outside the range. X is the number of trials. You're wanting 4 out of the range, 4 successes. Going back to the formula for negative binomial, then we need to use this. R is the number of successes, which means bad, it's outside the range. It's failure in that sense. 4, because we're after wondering whether or not the process of manufacturing these flares is going wrong. So R is 4, X is going to be 5. The probability of success is the probability of being outside the range. There was a 68% chance when it's working good of being inside the range from 14 to 26 minutes. Average burn time being 20 minutes. So your probability of success is not 0.68, it's 1 minus 0.68, 0.32. So you need to use this formula with these numbers. What is f of 5 in this situation? Using this formula, it's 4, choose 3. P is 0.32, so 1 minus P is the 0.68. To the x minus r power, 5 minus 4 power, times 0.32 to the r power. 4 choose 3 ends up being 4. This is a 0.68. And you got 0.32 to the 4th power. That's about 0.01048576 times 4 times 0.68, giving us the answer of 0.0285. That is the probability that x is 5. It's really the probability that x is 5 if the manufacturing process is working normally, as it should. Think about this. If this manufacturing process for the flares is working as it should, your chances when you're doing your sampling that it takes 5 samples before you have 4 flares whose burn time is outside the window from 14 to 26 minutes. That probability is small if it's working properly, if the manufacturing process is working properly. So if it happens, a rare event has happened if it's working properly. So we think it's not working properly, perhaps. Say that again. What I just said there, the last 30 seconds, is the key to what's called hypothesis testing in statistics. We have something called a null hypothesis. The null hypothesis is the manufacturing process for these flares is working as it should, normally. Maybe I shouldn't use the word normally. As it should. This probability being small means that if it's working as it should, observing a value x equals 5 would be rare. Meaning, observing 4 failures, so to speak, outside the range, at least, successes in this context, by your 5th trial, your 5th sample, is an unlikely thing to happen if it's working normally. So if it happens, you think it's probably not working normal. It's kind of convoluted logic, to tell you the truth, but it is standard statistical logic of hypothesis testing. And so we would reject the null and we think it's working improperly. We need to fix something with the manufacturing process. We're not really going to emphasize that logic until November. But when we get to it in November, it's going to be our main thing. Hypothesis testing and confidence intervals. So good to get a little feel for it right now. As far as using technology here goes, it's tricky as well because, again, and with the technology, it's programmed to do it differently than the way the book does it. E equals neg binom dist in a spreadsheet. You can see it's saying number of failures, comma, number of successes, comma, probability of success. Remember, success here means it's outside the range. Failure means it's inside. Our X was 5, and we had 4 successes, so to speak, outside the range. So there's 1 failure where it was inside the range. 4 successes, probability of success is 0.32. Same answer. Mathematica is also programmed that way. To actually calculate a probability in Mathematica using a distribution, you have to start with PDF, even though we call it PMF. Just keep things simpler to merge discrete and continuous distributions here and use one symbol for it. Negative binomial distribution. If you're not sure how to use it, the information button there that comes up, there it is, can be clicked, or you can go to the help center by Also getting there through the help menu, documentation center. Negative binomial distribution, n comma p are the parameters. What those mean, you should check the details. Again, looking here. N is a positive integer, p is the problem. Okay, n is the number of failures. Oh, no, excuse me. X is the number of failures. The whole thing kind of represents X. Probability of success P before n successes occur. Number of failures for us, that was 1. N successes 4. Probability of success 0.32. So we should replace the n with a 4, the p with a 0.32. And the thing we plug into the PDF, so to speak, for X should actually be the number of failures, 1. There we go. Confusing, right? This is the number of failures, or excuse me, successes in our 5 attempts. There's the probability of success. There's the number of failures. In the spreadsheet, the number of failures was first, the 1, then the 4, then the 0.32. And yeah, the number of successes and the probability of success are what go inside here. And then you put a comma and you put a 1 for the number of failures inside the PDF. Yes, kind of confusing. If we're going to program the actual distribution, the PMF here, in this situation, we will replace the 1, the number of failures, with X. And we could graph this as a discrete plot as X varies from, what would it be here? I guess it could be arbitrarily large here, but the probabilities are going to get small. That's a plot of the values of this PMF for different numbers for X, X representing the number of failures, not the number of trials. Our book does the number of trials for X. Most technology does the number of failures. It's just a different way of thinking about the variable. I'll show you how it's phrased in the other book that I got here. The situation for a negative binomial distribution here is that they call the variable M, and it counts the number of failures prior to the Earth's success, rather than the number of trials until the Earth's success. Just a different way of looking at the same thing. There's 5 trials until the 4 success, 1 failure. For us, X was 5. That corresponds to M equaling 1. R equals 4. The formula for the PMF is written like this in this book. And if you look this up on Wikipedia, you'll see it this way. PK is the probability that M equals K. That's the number of failures. K is the number of failures when you have R successes. This looks pretty similar to our formula, doesn't? With some differences. There's a something choose something else. There's a P to a power and a 1 minus P to a power. How does this correspond to our formula? Evidently, comparing what you see with the choose here, evidently R plus K equals X. Yeah, R is the number of successes, K is the number of failures. Add R and K, you're going to get the number of trials. So R plus K equals X, which means the power of 1 minus P changes from X minus R to an R. R plus K equals X. If you replace this X with, I meant here, if you replace this X with an R plus K right there, R plus K minus R, the R's cancel, giving you a K, matching the K that you see right there. Okay, so this book has this formula for the PMF. Wikipedia has this formula as well as a standard reference to look up. Can you use a spreadsheet or Mathematica on the test? Not really. So on the test, if I have you do this, I probably will, you'll need to use this formula as it's written. Funny thing about this formula, since X is the number of trials, is it doesn't start at 0, it starts at R, because you're assuming R successes. Whereas with this formula, K is the variable, K starts at 0. K is the number of failures. It could be 0 failures. It's kind of confusing that they use both an M and a K for the number of failures. Would have been better to use a lowercase m here or a capital K there.